Much, and thanks everyone thanks for the organizer to inviting me, and for all of you to be here to listen to poster something is not your main field of work. So I'll promise to give you a very gentle introduction to the world of supernovae. So by the end of the talk, all of you can decide to change and rapidly start to work about supernovae, because they're the all important things in astronomy. Kidding. Or maybe not. First, I'll just introduce the standard scenario of supernovae to understand what we are right now, what we know, what we believe we know, and then I'll move to what has been basically the area of my studies from the first postdoc up to nowadays, to everything that goes beyond the standard paradigm of supernovae, telling also you a little bit of what we know about these extreme supernovae nowadays and what lies ahead in the future. So the first part is the classic scenario. So if you're not a supernova lover, or you do not love very big cosmic explosions, you will be happy to remember that there are two main mechanisms in which a star can explode. The two main mechanisms are the thermonuclear and the core collapse. In a thermonuclear case, you have two stars. A white dwarf, you always need a white dwarf, and then you have a companion. These companion stars in a binary system can be a red supergiant, usually, or it can also be another degenerate star like the white dwarf. In the case of the first one, it's called a single degenerate scenarios, where the white dwarf, due to the force of gravity and the proximity of the companion, it gets all the material from the companion until it will reach a certain level of stability and it will explode as a thermonuclear supernova. That because, as a lot of people knows, white dwarf was paradigm of stability. If left alone, they will never change their status. They will always stay white dwarf forever and ever, unless they have a companion or they have another white dwarf nearby. And the two white dwarfs, they exercitate gravitational attraction to each other, and they will eventually spiral towards each other. They will crash, and that crash will release an energetic wave which will trigger a thermonuclear explosion. Both cases, same kind of explosion. The core collapse is much more intuitive. It goes for massive stars, and at the end of the lifetime of the stars, the perennial fight between gravity and pressure will be won by the gravity, because there will not be any more nuclear reaction in the star left to create nuclear pressure. Both of those are centripetal forces, which goes towards each other for the entirety of the stars. At that last moment, when there is no more nuclear reaction, the pressure will just fade away. The gravity will win in less than 1 nanosecond. The entire star will collapse in one single point, and then will bounce back into the cosmos, producing new elements because of the high density and the high energies in these bands. As you can guess, there are a lot of stars in our cosmos. There are different stars, different size, different stellar evolutionary paths. All of those lead to core collapse supernovae. So the variety of core collapse supernovae is much more different than the one of thermonuclear. So these two are the mechanisms for stellar explosions. But how this stellar explosion looks like, how can we disentangle which one is what? So if it's a thermonuclear, it's a core collapse of a Wolf-Rayet star or a red supergiant. So what we usually do in terms of supernova in extragalactic transient astronomy, we take photometry, creating what is called the light curves, which tell us about the luminosity evolution of these explosions. And we also get the spectroscopy, which provides us with information on the chemical leads hills of produced in the supernova explosions. Both of them are unique for each one of supernova. They are a striking signature in both cases of what kind of supernova it is, and as a consequence, what mechanism has created this supernova. However, all of these, the luminosity of all these supernova is driven by radioactive decay. About these isotopes of nickel, the nickel 56, we can only be produced in a supernova explosion because it needs the high density that you have triggered by the explosion itself. High density, high energy. These nickel 56 has a decay time of 6 days, and they will release photons. These photons are the one that drives the luminosity evolution. the one and the one of the daughter nucleus of cobalt 56, which will eventually decay in iron 56. So all the main principal producer of the luminosity of a supernova evolution is the radioactive decay. However, when you have core collapse, for example, red supergiant, you also have hydrogen. These photons of the decay, each the hydrogen layers, which recombines, and you get an additional luminosity which provides a slower decline, like this one. In these plots, in the y-axis you see increase of luminosities, in the x-axis you see the days after explosion. This is roughly 1 year time scale. Overall, in a simplistic way, if you want to describe the supernovae, the brighter it is, wrong button. The brighter it is, the more nickel has been produced during the explosions. The larger, the slower it is the time scale, the longer the time scale, the more mass has been expelled. The mass expelled cannot be created. That's the mass that was originated from the progenitor star. So a more massive stars will lead to a longer lasting supernova. Stars that create more nickel, it will create a brighter supernova. That's usually overall how does it work. There is a relation between the two in both the mechanism. It has been studies that basically no more than 30% of the entire mass of the star can be converted in nickel. So if you have, for example, like a 10 solar mass stars where at the explosions, you cannot not have more than 3 solar masses of nickel, and that is already an extreme. So that is the maximum nickel that can be created. So you cannot have 100% nickel driven supernovas, which is only created by nickel, because not physically possible. You don't have the chemical yields, the chemical seeds to create that much of a nickel in any kind of stars, regardless the explosion mechanism. To diversify between the light curves and between the thermonuclear and the core collapse supernovae, you also need at times a spectroscopy showing all the chemical signature of the supernova evolution. The thermonuclear one are the only one able to produce a strong amount of silicon and sulfur, while if you see hydrogen or helium, it becomes from a core collapse supernova. And if you think about it, it is kind of straightforward, because in thermonuclear you need a white dwarf and a companion. There is no hydrogen over there. You should not see hydrogen, while in a core collapse supernova you have a red supergiant, a yellow supergiant, a blue supergiant. They finished the color. There are no other supergiants as far as I know. There are only these 3 colors. And you can have a Wolf-Rayet stars that lost the hydrogen, and then you have the helium, and so on and so forth. So, but how this translates nowadays? So nowadays we have a lot of discoveries. We have roughly more than, I think the number is 80,000 possible supernova discovered per year, with 24,000 supernova confirmed supernova discoveries in 1 year, with only less than 10% spectroscopically confirmed, which is what we want. We need the spectra to understand which supernova it is. And if I'm interested in thermonuclear supernova, core collapse supernova, I can follow it up. Because remember, supernovae are catastrophic events. It means they happen only once. Every single day of a supernova life is a different level of physics, because these are expanding black bodies with change in temperature, change in densities. They will change also on the ionization, the chemical yields, and so on. So every single day is a different physics, and it's very complicated if you don't have spectra to understand the physics. You can only guess what is going on from light curves, which still are very, very, very useful. So this is how it looks nowadays, light curves. So there are now a lot of surveys that explore the night sky multiple times, patch of the night sky multiple times in the same night, like the Zwicky Transient Factory or Pan-STARRS or Atlas surveys. Gaia has done the same in terms of a space telescope. There are at least 5 to 6 surveys. And this is what they do. They get usually information in 2 different filters. The green one is the G filter, the red one is the R filter in the SDSS filter scale. And you can actually see this is the rise time of an object and this is the decline. This last here is one of the LSST broker. If you're not familiar with the name, the broker are all these LSST approved tools that will follow up transients and any other object that is going to be discovered by LSST and will provide to the community in form of both web tool or Kafka streams or other way of streaming or streams that you can get straight into your mailbox. This one, it was this object over here. If you can see here, this is a rise time of more than 100 days. If you saw before, from this one, all standard supernova have a rise of like a few couple of weeks, and only the 87A, which is a blue supergiant, have roughly 70 days. It was for the peak over there. So that is one of the objects I'm going to talk about later on. The other way that we need to understand what supernova is and how can we get more information about the physics is the spectra. And what we do is usually we get something like this at the telescope and say, okay, this is a promising candidate, looks like a supernova, is rising of at least 2 to 3 magnitudes. And apologies for all of those you do not use these pesky numbers like magnitudes, and they are more aficionados of like luminosity or flux density. To give you an idea, 1 unit of flux density is equivalent to 3 magnitudes, more or less. So 1 order of flux density is 3 magnitudes. The other things we get are the spectra. So we go to a telescope, we say, okay, this is a good candidate. We trigger a spectroscopy. We get the spectrum, which is the black one. And what we do, we compare with a lot of libraries of spectroscopy. These are 2 examples of very old fashion spectral classifier. This one, it was devised by the Italian, and it's called Gelato. You can see the combination here, over here. And this one, it was an old one, is written in Fortran, and has been devised by 2 scientists, a French one and a US one. This one it needs to know the distance of the supernova. So there is a limitation, but when you know the distance of the supernova, it gets far more precise. This actually, it can tell you also the distance of the supernova. So it's much more flexible. To be honest, there is also another good mention. There is Astro-Dash. It was produced by Casey previous students, Dan, which is also very good, and apply machine learning to discover what is the likelihood of this black spectrum to be associated with some kind of supernova. If you combine these information like curves and spectroscopy, going back to explosion mechanism, we were just 2. Remember, we're astronomers, so we like to mess up in terms of naming scheme. This is what's happened when you lead the astronomers, not the physicists, to do the naming scheme. So with only 2 mechanisms, we decide to give all these fantastic names based on, at the beginning, the appearance of the light curves, then a mix of light curves and spectroscopy, then only spectroscopy only. So it's very complicated. This has actually been an addition. I just changed it the other day because from 2023, now we also have the 1CN, which they were discovered for the first time previously. Bottom line, the thermonuclear are only the 1A. So the problem is that the 1 is for anything that doesn't have hydrogen. So 1B and 1C is a core collapse. So 1B is a core collapse, it doesn't have, there's a little bit of hydrogen. 1C is a core collapse, it doesn't have hydrogen, but shows helium. However, a lot of times you will see that, I'll show you in the next slides, spectra, they show not only the standard lines of supernova, but they also show these emission lines. The standard lines of supernova, which has an absorption a little bit bluer than the lines, and a big emission, is called a P-Cine profile, which is the hallmark of a co-moving material. Is the standard profile you see in supernovae. Always remember, P-Cine is not a supernova, it's a luminous blue variable, and is where it has been seen for the first time. Because it's a co-moving frame, it was the material expelled by the luminous blue variable into the cosmos, and at a certain velocity, which is usually for LBBs is around 1,000 kilometers per second or a little bit less. So this is the standard profile you see. This is a type 2 because it's hydrogen. A little bit of hydrogen, a little bit, far less, but more helium is thought to be a 2B. Then you do not see hydrogen is a 1B. You do not see neither the helium is thought to be a 1C. And this is for the core collapse. However, Stars lose mass. We see with our sun, we see basically in any other star. Some they lose more, some they lose less, some they lose close to the explosion, some they don't. However, when there is a lot of material, what happens is that you have the supernova explosion with all the material going into the cosmos, but they found some other material was there before them. You get two materials colliding into each other, you create shock waves, and you create a lot of electroscattering. So what's going to happen is that the usual profile of a supernova, which is basically a black body emission, because it's like a black body, because it's very opaque, the inside of a supernova, so it emits like a black body, and what you see are just the lines that are on the optically thin layers which are around this photosphere. It gets completely squashed out by the electron scattering, which are also further away from the center, and what you see is not a black body anymore. You see just the product of the electroscattering with these emission lines, which are Lorentzian lines, aka the wings are coming from electron scattering. If you see these narrow lines, what you see, these emission lines are a composition of different layers. There is the unshocked material which is outside, which hasn't been reached by these shock waves, because when you have two materials which collide, you create two shock waves. One goes inside, one goes outside. The one goes outside is changing the velocities of this material, which is called circumstellar material, until there is still going to be part which is untouched. So what you see in this line emission, you see the untouched part of the CSM, which is basically the velocity of the wind emitted by the dying stars, which tell us as a constant what was the stars, if it was a Wolf-Rayet, a red supergiant, or a LBV, because they have different wind velocities. And then you see the shocked CSM and the shocked ejecta, which is this material expelled by supernova, and you do not see the ejecta at all because you have no idea, it's completely covered by everything. So if there is hydrogen, it's called 2N. N stands for the narrow lines. It's again an observational nomenclature. 1BN is because you have the helium 1, and this one there is no 1CN. The 1CN are, if you see these narrow lines, come from basically carbon, nitrogen, oxygen. Remember always the shell structure of stars: hydrogen, helium, carbon, nitrogen, oxygen has been deprived of the first two lines. However, interaction is far more complicated and more frequent than we thought originally in the two scenario paradigm, because what we start to see is that the more supernova we have, the more supernova we probe spectroscopically, the more strange things we started to see. Like this was a 1Cs. These spectra, they don't have hydrogen, they don't have helium, they have like silicon, and then they start to change later on, like at what we would refer as a 2N. The supernova doesn't change. Is that what we saw? It was a normal supernova that's finally cooked up with the hydrogen-rich material, which possibly was both the hydrogen and helium-rich material that has been expelled, but it was not homogeneous. It told us basically that the explosion itself and the mass loss had an axis of preference. So it was close to be a ring, because otherwise we should have not seen the original supernova. We should have seen already the interaction. So these kind of combination tells us also a lot about how stars lose their mass, how massive stars lose their mass, and also about the geometry on how these stars lose their mass. That is the standard. So how do we move from there? So almost 10 years ago, Sri Kulkarni made this plot, which is usually referred to the supernova parameter space. You get, again, the pesky magnitudes, this time a little bit more gentle from my point of view. I put the luminosities for the 8 magnitudes and the time scales. If you put all of the thermonuclear supernova at one end, all the core collapse supernova, this is the nucleus of all the supernova that we knew until 2010. This is all the kind of supernova we found. And these are basically, this is your map to understand. As I told you before, the more the nucleosynthesis, the brighter it goes the target. The bigger is the mass, the wider it goes. It doesn't go very straight, it goes a little bit in this direction. And then you have other things about the velocity, so the energy of the explosion itself, or the opacity of the material, or if there is dust, everything goes down. So this is kind of your compass to understand this parameter space. The limit, which I mentioned before about the amount of nickel produced by supernova, can now goes beyond the 30%. are these two lines. The solid line, as you can guess, is for thermonuclear. The dashed one is for core collapse. So everything goes higher than this should not happen. And of course, natural. As soon as we think something shouldn't happen, nature say, ha, you haven't understood the bloody things, and this is why it's so fun to do research. What we started to find are two big families of objects, something which are very slow and very bright, which with absolutely no fantasy at all, we call them superluminous supernovae. And the other one with a little bit more fantasy, we call F-bots, that stands for fast blue optical transients, which are, on the other hand, very varied. They vary 6 magnitudes, so 2 orders of flux densities or luminosities, but they're all very fast. See, this one is a semi-log scale. If you are familiar with the kilonova, which is the Newton-star merger linked to gravitational waves, the kilonova is basically here. Is a very, very, very short rise time, but it's very faint. These were slightly longer, around an average of 5 to 6 days to rise to the maximum, but they can go very, very bright, up to minus 22. So it's basically up to almost a luminosity of 44.5 in logarithmic of 10. What can they be? So that was part of understanding to go beyond the standard scenario and understand what are these extreme. We'd always bear in mind that what we learn also from a lot of observation is that interaction, which has this red cycle, can basically do everything. Can do everything except not really fast, very, very bright, and not very, very slow and very, very faint. So those are the only two things interaction cannot do. For the rest, it can do everything. But it comes to a price. You should see some signature in the electromagnetic spectrum of this interaction based on what it is our understanding. So we started to probe first these superluminous supernovae, which you can actually see here the full light curves compared to what are the light curves of normal supernovae. So this is a combination of 1A, type 2, 1BCs, and these are the superluminous supernovae. At least 5 to 10 times brighter, 5 to 100 times brighter than normal supernovae. They last much longer, and because they are much brighter, we can got spectra up to redshift of 2. You have to think about type 1A supernova cosmology. They got spectra up to redshift of 1 and something. All the others been 1.3 or 1.4, while all the others been photometrically confirmed up to redshift 1.8. These has been photometrically confirmed up to redshift 4. So it's double the distance. And the other interesting part is that all these superluminous supernovae, they explode in very low metallicity environment, which are the one you expect to see at higher distances. And that makes very appealing in terms of cosmological sources and cosmological probes, because if they only got to explode in low metallicity environment and they're very bright, we can finally, for the first time, explore the rest of the very far cosmos in terms of stellar explosions. The question was, are these thermonuclear, are these core collapse, and why these are different from the standards? Because we knew now finally what to look for, we started to find more and more and more. And that tells a lot about the bias in the decision of people and understanding what they want to research, because they were very puzzling and very, very bright, so they could give us a lot of information about the high redshift. We basically now identify, since the first superluminous supernova in 2010, so after 14 years, we identified roughly 200 superluminous supernovae. Just to give you an idea, the 1B, 1Cs, they are coming from Wolf-Rayet stars, we had roughly 80 to 90 good, well followed since the 80s. So they have we knew now what to search, and we massively decided to look for something to get more and more information about these new ones, because they were far more interesting. And what we realized that of these superluminous supernovae, there were actually 200, we realized there are 3 different classes. There is one, the red one, which has hydrogen in it, and it resembles a lot the standard core collapse, but it's brighter. And there are 2 that don't have hydrogen or helium, but they have completely different time scales. This is as a rise time of roughly a month, and these kinds of rise time, which is, goes between 50 and 100 days. And almost the majority of them, they shows these little bump before the original part of the light curves. While the F-bots are far more recent, they're like 5 years old, kind of recent. We also get a good bunch. We have roughly more 2 dozens of them. You can see they are much varies, but what they make in common is that basically by the time they reach their maximum luminosity to when they decade, they reach half of their peak luminosity in less than 12 days, which this usually happens in supernova after 3 months. So this is much, much short-lived, so it has to be something different that cannot be explained by those 2 mechanisms, regardless of the source. That brings to the fun part. Okay, we got new things. How can we disentangle what they are? What do we believe what they are? The first idea come across to mind about superluminous supernovae was the peristability. Peristability, and for all of you that are theoreticians, it would be amazing to know that all the theoretician groups working in supernova, they were absolutely in agreement on how a supernova coming from a peristability should look like and what should be their signature. All of their models, they do the same information because it comes basically from an enhanced pair-positon couple, which basically trigger the explosion of a very big stars. With very big stars, I'm talking of stars with a core helium mass of higher than 75 solar masses. And that is just the core. So the entire masses, they can reach up to 200 to 300 solar masses, which is what you expect would be the first stars in the universe. These are far, these are what they should be. There are only 2 catches. All these models for peristabilities, they needed 0 metallicity, not low metallicity, 0 metallicity. Second one, these are basically gigantic fireballs. They produce a lot of very heavy atoms, and as such, they should be very, very rich in nickel production. So if you take the nickel production that is needed to reach this peak of luminosity, this is the decline you would have get it. They were bright, they were slow, but they were not still slow enough for apparent stabilities, and they were not in the right environment because they were at the environment like the small Magellanic Clouds or the large Magellanic Clouds. So low metallicity, but not 0. There are now far better candidates for peristability, which I'm not going to talk about because otherwise it's going to be far more than 1 hour, this talk. So we came with 2 main ideas: the always present interaction, which was able to describe something like the luminosity evolution, the temperature evolution, because as I said before, this is an expanding medium, and like any explosion, by the time passes, the density is reduced because the volume increases and the temperature reduces as well. And the differential velocity, which is something I'm going to show you in a little bit. Then we came up with another idea. What if these are normal core collapse supernovae and the products, so the core collapse supernova, what I forgot to mention before is that when you have core collapse, when you have a thermonuclear supernova, the remnant gets destroyed. The white dwarf gets destroyed. While when you have a core collapse supernova, you create a new remnant, which is the neutron stars or the black hole. Usually if you have a black hole, so you have a very faint supernova, or what are called failed supernova, because the black hole recatches part of this material and not all the energy is able to escape the gravitational pull of the black hole. This doesn't happen with neutron stars, and is where you create all the core collapse supernovae. So what if the neutron stars of the created by this explosion is actually a magnetar? A magnetar is a very fast spinning neutron stars. It spins as fast as the pulsar, but has a magnetic field of 10 to the 14 Gauss. So it's much higher, is at least 3 orders of magnitude higher than the magnetic field you would expected by a very fast spinning neutron stars. These basically create a magnetorotational energy that goes as a kind of a wind. It goes towards the ejecta, which has been moving, is the materials of the star of the explosion has been moving towards the cosmos. It gives an additional energy that is converted into luminosity. And what it does, in principle, the magnetic field will lock the evolution will change the chemical evolution because it will not allow these temperature to change in the same time scale because of the conversion of energy. And in fact, it's something we saw in the electromagnetic spectra. So these blue and black are two superluminous supernovae 30 days after peak luminosity, so they're already declining. But the temperature and chemical evolution is basically, if you see all these wiggles over here, are the same one of this orange one, which is a type 1c, is a peak. So 30 days of difference, completely different temperatures. They should have completely different temperatures. They should have completely different masses, aka completely different chemical yields, but they look the same. So there was something fishy. There was something like, it looks like a core collapse, completely misplaced in times and energy. So this is why we thought, okay, this might be core collapse, but there is something which is changing the energy budget, and it's also changing the evolution of the spectrum. And that's something that the magnetar could do, while the CSM, as far as we know, it cannot do because you have these extra narrow lines that should show up as additional energy. So that was the one of our idea that is still the most popular, and we came up with this idea back in 2013. So I said to you before, they're bright, we can observe them far enough, and if they are actually core collapse supernovae, we can probe the evolution of massive stars up to high redshift. In principle, up to redshift 10 with JWST, with the main issue is that JWST should need to catch it as a discovery service, which is really, it can only happen by chance. If someone else is observing some part of the sky and they're re-observing again, we can see that there is a difference in the images, and that is the supernova. So it can only do in their way. So it's potentially up to redshift 10, but most likely it's up to redshift 4 with LSST. However, with the Dark Energy Surveys team back in Southampton, we thought, okay, we know these are bright. We know that we can observe very far away. So should we try to see if they can be somehow standardizable like the type 1a? And remember, these are all these, when I say standardizable, so type 1a are not standard candle, are standardizable candles. So you need a mathematical relation to make them standard, to look like all of the same. So what we found, there was a very similar relation. So there was a very tight relation between the peak luminosities and the decline over 30 days, while for type 1a is over 15 days, in a bluer band, all in blue bands, around 400 nanometers or 400 angstrom, if you prefer the angstrom. And using that mathematical relation, you could in principle standardize the superluminous supernovae, all of the three that I showed you before, of these three, it would have been this blue one. So the one that don't have hydrogen, but they are the faster one. Again, faster, it means rise time of 30 days, decline time of 1.5 years. Which surprisingly also one of the, for which we have more signature about this magnetar, because we did the semi-analytical analysis and we reproduced this decline, and this tail is up spot on with the release of magnetar energy at the end of when the jet has been completely optically thin. It is spot on, the decline is there, and it's true for any kind of superluminous supernova. So we decided to use them as standardizable candle, and we use 20 of them, and we create the first sample diagram of superluminous supernova, comparing them with 1A. For those of you that are knowledgeable of supernova 1A cosmology, you will know that JLA is kind of the old player in the game, because now there is the Pantheon sample that reach up to 1.8, and there are far more supernovae, there are a lot more. We use the JLA, not because the Pantheon was not available, but because the way that has been standardized in the Pantheon is different from this JLA. We use the same methodology of JLA, so we say, okay, we have to at least to compare pairs with pairs and not pairs with apples, so we use compare with the same methodology. And what we found, it was basically we had a scatter of 0.27, which is fine. These are 740 type 1a supernova. These are 20 superluminous supernova. I wouldn't expect to have less, but we get roughly the same values of the blue dashed lines. It was the best fit in terms of omega lambda, omega m cosmological scenario. Of course, we did these also for the WAWO, and we got very similar to what it would be if we use the Lyman alpha break galaxy at high redshift. So that is promising. It has to be seen if with more data we can get always the same values. It is promising because they're bright. They're there. We can see up to high redshift. They go in low metallicity galaxies, aka there is very low dust content, and dust has been always the main problematic in terms of systematic errors for type 1a supernova. When you do cosmology, you have two kinds of errors, systematic and statistics. Statistics, as says the name, you can improve those errors if you get more and more targets, like type 1a supernova. The more they get it, the better, the more precise were the measurements. Systematics is something you cannot change. It can be the filter measurements, it can be how you measure them, or it can be your physical knowledge of the objects. They can be not correct. And this is what basically stops at the moment the superluminous supernova rather than the statistics. If you could have more, we could have more precise. But we have far less systematics. The only systematics we have for superluminous is the understanding of their source. So LSST in this case will be very helpful because we'll discover a lot of these superluminous supernovae, and we will finally see if we can use them as additional cosmological probes. So what about F-bots? As I mentioned you before, their luminosity is different from the superluminous. Superluminous were almost at the same luminosity, around this minus 21, which is almost 43 of 10 to the 43 ergs per second. These are much varies. When you have that kind of difference, it cannot be one single mechanism. It cannot be one single scenario. You need something that differentiates them much. So ideally, we are talking about three different kinds of groups: high luminosity, medium luminosity, and low luminosity F-bots. These are, what I listed here, are all the major theories that have been behind these F-bots. The main issues over here is that they are very fast. So by the time we point the telescope at them to get a spectrum, they are already like 20 days after, or even 10 days after. And that's very hard, especially because up to 10 days, they're completely featureless. It's a blue-black body, very hot, and you don't see anything. We have spectra only for one, which it was 18 Cow, because it was very, very nearby, and it was also one of the brightest, as you can see here. It goes up to minus 21. They were brighter, but they didn't. These are very old objects, and this is an object. It was from the Dark Energy Survey. It was a redshift 2.4. So the spectrum was like, okay, we know the redshift because we can see the lines from the galaxy, but it was no more than that. It is interesting to see because some of the lowest one in terms of time scales, about rise and decline and luminosity, are in the region of the neutron stars black hole merger, for which we do not have a counterpart, and we didn't either have new gravitational waves coincident with the neutron star black holes, but it could actually be one of these F-bots are actually neutron stars black hole mergers, while others has been suggested to be neutron stars white dwarf mergers. So these are also important because we can get now the depth of massive star again across cosmic history if these are massive stars, but even more important, they could be the aftermath, the lower ends of compact star merger. And we could already, because all of these have been observed, this was again observed by DESS. It was a redshift 1 when LIGO was not on, and LIGO doesn't have a sensibility to get a neutron stars black hole. Neither a LIGO nowadays has a sensibility to get a neutron stars black hole a redshift 1. But if we get one of these at the redshift compatible with LIGO, and then they look alike in terms of light curves with this one, that means we are getting the neutron stars black holes merger at high redshift the LIGO, and we can get that even without a gravitational wave figure. So, as I mentioned a few times in my talk, these are very exciting. This is completely new because they're still not secure, and they help us to understand the depth of massive stars across cosmic histories and compact star merger. But what about interaction? I said before the interaction can make almost everything, and we are only limited by our understanding of interaction, because we haven't seen multiple ways of interaction. If you remember, I said that the basically circumstellar interaction, if you increase the circumstellar interaction, is basically an in-between the nucleosynthesis and mass. So I did this kind of exercise with one kind of superluminous supernova, the one that have the bump at the beginning, because surprisingly, we got interacting supernovae with a bump at the beginning. And that is basically just the supernova that explodes and get the first layer of CSM, and you have this brightness, but is low, and then it keeps going on and gets the more massive layers of CSM, and that's what powers the main peak. So there are just 2 layers of stellar mass loss, which is not really unusual in stars. We know that they can do it. We know that if they have instabilities, they can release in different time scales. We've been seeing this with Eta Carina all the time. It does that. So why can it be that some of those are actually very powerful circumstellar interaction? So what we did, it was do a very simple, easy thing. Since this is like an in-between the two, if I multiply a light curves of a supernova by the same time in terms of stretch and energy of a type 2n supernova, how does it look like? And this was actually one of the supernovae that have also this bump. The time scale and luminosity and also this kind of ondulation you see over here are identical to one of a interaction supernova. And this ondulation in the luminosity evolution, it basically means you have, every time you have an additional energy of energy, it goes up to give you more energy, more photons, and then it goes down because it's finished. And then you get another one, it goes up and it goes down. So a magnetary is a constant release of energy. You can now switch it on and switch it off, switch it on and switch it off, especially because they're spinning very fast. So there is neither an angle point of view. It has to be always the same angle. But these can actually happen if you have different density cluster of circumstellar material, which again has been seen in massive stars. You have usually 2 different layers of circumstellar material, one a little bit dense and one less dense. And the one that are denser, they go as clumps. And these are all consistent with small clumps of 0.2 solar masses of material, which is something you can get from normal core collapse supernova. So it might be, and the same goes for the fast transients. Some of the fast transients, in terms of speed of their evolution, they are identical to, which are the gray, they are identical to the orange one, which are the 1BN of before. So again, are interacting supernovae. The main problem is that they were too fast or too far, and we didn't get a spectrum. However, for one of those, we got a spectrum later on, which I'm going to show you in the next slide. And again, here, we have done, that's a work in preparation, we have done another phase diagram of supernova. This is the rise of the magnitude versus the color. And these two over here, down here, the star and the square, these are the superluminous and the 2N. They are very, very similar in terms of temperature evolution. They get blue, they get very constant for a long, long time, which you could do even with a magnetometer, but it's very curious. And then you have the 1BN here and the F-bots here. And this has been done 1 year ago. The 1CN are here. So that you can actually see there is a perfect straight line in terms of changing. This is how the higher it is, this one, the more rapidly changes the temperature, aka this material is not that dense. It gets it cools down very, very quickly. And we can actually see a line that there is always, the faster it gets, the quicker it cools, which assumes that it might be the same kind of mechanism. And the other things we saw is that when you have these shocks and you have the interaction, you have these two shocks that propagates in the two mediums. When the shocks are completely ionized, has completely shocked the entire medium, the luminosity, the additional luminosity ceases. You don't have an additional luminosity. And what you get is a decrease of luminosities. And based on the density, this can follow a set of Taylor phase, like the supernova remnants, or a snowplow phase. And you can actually see these are, the orange and the blue are the one for two different types of 2N. The different slope are due to the fact that it was, for one of the two, it was first all ionized the CSM, all shocked the CSM. For the other was instead the ejector was shocked more, aka the ejector was less massive than the CSM. And then you get these superluminous supernova which has a very, very similar decline between and in between these two. So we don't know how much of interaction there was actually be between if you combine this information and this information. But what we recently saw, this is one of the only late time spectra of F-bots, and these are emission lines of helium and emission line of hydrogen, as you see in perfectly as 1BN and 2Ns, is what you should have seen as a 1BN 20 days before. So that's this interaction. There's no other way to put it, because all the emission lines, they're not the PCD lines. And this is what we saw in one of the superluminous supernova, one of those that have those wiggles that I showed you before, and also the decline like 2Ns. You see these emission lines, which has roughly full width of maximum 100 kilometers per second, so it cannot be a galaxy. It is a little bit blue shifted as it should have been. Both the helium 5867 and the helium 10,830, same profile, same blue shift. I still do not trust the wavelength calibration, so it could be they're not blue shifted, but they're centered at the helium. But even if they're centered at the helium, the width of this line is too wide to be from galaxy. Has to be from the circumstellar material. It's 100 kilometers per second. If the calibration is correct, it tells us that not only there is circumstellar material, it is completely asymmetric, because you can only see the blue shifted component. So you have a huge cluster of material has been expelled before the explosion, which goes towards you, because it's blue shifted with respect to the centroid, the center of the stars. So that would tell us not only that there is a lot of circumstellar material, but it would tell us about the geometry itself of the supernova. The last bit, in the last few minutes I have it, the new frontier. This is my very biased way of surveying time domain astronomy. I've been the PI of this international endeavor, which is EPESO Plus. We got 500 nights of observation at a 3.6 meter telescope in ISO in La Silla, the NTT, from 2019 to 2024 to observe the transient sky. We have been extended up to the 2025, but we are linked to the new spectroscopic new spectrograph, which is going to be mounted at SNTT whenever SOX will finally be available. SOX stands for Son of X Shooter. It's basically a small version of X Shooter. It's a completely bad acronym. I didn't choose it, so I'm not to blame, but I always make fun of it. It's been delayed now for like 3 to 4 years. It should have been mounted and assembled already and started in October 2024. I know it's still in Italy, so that's not going to happen. So possibly we're still getting spectra during the time of LSST. LSST will start with the CAM in July 2024. Euclid already in the sky. Euclid can get is the only way they can get or superluminous. So the only supernova Euclid can get with their own standard deep surveys without any specific supernova surveys. They can only get two kinds of supernova: the superluminous and the peristabilis, because they're only two bright enough and long enough to be observed by the very not transient friendly cadence of Euclid, because they observe every month for 2 days, 3 days, and then they'll observe after 100 months, and they have a gap of 6 months in the schedule. So these one altogether, especially LSST and Euclid, will provide roughly in the next decades 1,000 and more superluminous supernova, and it could be nice to see if we can test this cosmology for goods, because now we will have first of all, we'll see if they're actually standardizable, because with 20 it could be a chance. It could still be there. It is hard to be a chance, but it could be there because of some errors we did in some of the reduction. But with 1,000 it cannot be. If it is, it has to be with 1,000. And then we can use those cosmological probes up to redshift 4. We will get 45,000 of these fast transients. How many of those can we actually get a spectrum? I guess if we get 50, we're going to be lucky, but less, still more than what we have right now. And really, really a lot of interacting objects that will allow us to understand better their phenomenology, and if they are related with the extreme of these of the panorama of supernovae. So this is what is going to happen in the next 10 years. We'll get a lot of data. So we are going to basically boost the factor of supernova discovery of more than 100 with respect nowadays. The bottleneck of all of this is that we do not have enough spectroscopic capability. So one of the things we thought to say, okay, how can we do it? There are different ways. One way is to get machine learning algorithms or AI algorithms will allow the classification of supernovae only from photometry, which we will have plenty. But again, for a lot of them is nice. You can say, for example, for 1A cosmology is nice because you say, okay, this is 1A, I can use it because I only use the photometry. But for all the others, we need a spectrum to understand what they are and to understand their population, their evolution across cosmic time. So something has to be done to identify very early, especially a lot of these core collapse supernovae. Another way that we did with one of my PhD students, it was, okay, we know that we are not going to get a lot of spectra. Let's assume we go with the most common core collapse supernova, which are the type 2, which are the hydrogen rich. Let's assume we get one spectrum, and that was the AI tool that Eleonora came up with, is a neural network that is basically from one single spectrum is able to create the entire time series of spectra starting from one single spectrum. So even if you haven't observed spectroscopy, but you have the photometry, you can recreate the entire spectroscopic evolution of any kind of type 2. And this is important because, as I told you before, every single moment in terms of physics of a supernova is different. If you want to understand them as a population and then getting the information about the progenitor stars, aka these massive stars across cosmic time, you always need the same physical paradigm. You always need the same physical status, aka you need the same phase in their evolution. A luxury that you cannot have it unless you have a tool like this. And this actually shows you that the later you get in terms of spectrum, the more precise it is. It's not that precisely reproduce the early spectroscopy, but you can actually see these are also the velocity, aka the full width of maximum of this absorption line, and also the full width of maximum of this hydrogen alpha, but also the iron lines, which are here and here. And these, you can actually see the predicted lines are all these lines from all the neural net models, and the crosses are what we observe with the original spectrum. So these, it takes only one spectrum, is assuming we do not know any of the others, and it creates all these lines and all these spectra. And so for this one, the attempt, it was the original ingested spectrum, was the blue one, and the black one are put here just to compare if we actually would have done a really good job, which from my point of view, it really did, with the same strength, almost all the lines, and the right evolution feature. So not only he developed the lines in the strength, but also realized which lines, what elements would have been happening at the right temperature and so on. One of my other PhD students is developing a code to get more information out from the light curves of core collapse supernovae, especially because it created two new tools as a Gaussian process that is able to augment the data available for a normal supernova, reproducing the entire light curves without having the needs of all the data. But you also create an analytical process to add an additional shell of circumstellar material, which we know it is in a lot of core collapse supernovae, to try to reproduce all of those, all the light curves coming from core collapse supernovae. Then there are other two students for which they recently started. Karis is working on both F-bots and superluminous supernovae, while Callum, that recently started, is looking at interacting supernovae, especially 2Ns and 1BNs, as a function of their environment, because something we still do not know. So that's all for me, 2 minutes to the end. These are the key take-home messages with what I said so far. I will also leave you to one of the things I really care for. I'm also a huge fan and ally of any idea in matters. This is one of the campaign we did in Cambridge. I've seen some of the one you've done here. This is for the unsung-ish heroes, because some of you might recognize Albert Einstein over there, which are all people that come from minorities or are disabled. Albert Einstein had dyslexia and dysphasia, So it's as close as you can get to a neurodiverse student or neurodiverse science. Very few people know that that guy over there is Gustav Kirchhoff, father of the circuit law, was basically paralytic, not able to have motor disability for more than half of his life. He was always with crutches, but all these portraits are actually when he didn't have crutches. And if you see, he was always holding with something because he could not stand. So just to give you a lot of other very important, like Malva over here, she's a queer, as she defined herself, is one as a queer person of color, and is one of the leads in gravitational wave science, and is the first science dean at the Massachusetts Institute of Technology that was not a white man. So there are a lot of really, really great scientists across the world. We might not know it, and it's very good to give them a role model to our students and also to ourselves to see how a lot of different people can succeed in making science better. And that's all.